Welcome, everyone. It is my extreme pleasure to be hosting this first panel of the Breakthrough Prize Symposium 2020. The panel is entitled, Will Black Holes Give Up Their Secrets to Science? So we will look at some of the secrets they have already given up, and perhaps which other secrets are possible in the future that they may give up. So joining me on the stage are people who are kind of inspirations of mine, people whose work I have covered in videos on YouTube. So I'm so excited to introduce, to my left, Shep Doeleman. He is an astrophysicist at the Center for Astrophysics, Harvard and Smithsonian, and a project co-leader of Harvard's Black Hole Initiative. He is director of the Event Horizon Telescope Collaboration, which won the Breakthrough Prize in Fundamental Physics for producing the first ever photograph, I don't know if we'd really say photograph, but an image of a black hole. Next to him, we have Andrew Strominger. Andrew Strominger is a theoretical physicist at Harvard University. He has contributed to numerous advances in string theory and quantum gravity, including groundbreaking work on black holes, and he won the 2017 Breakthrough Prize in Fundamental Physics. So he will be representing sort of the theoretical side of physics for this panel discussion. And on the far end, we've got Samaya Nissanke, who is an astrophysicist and spokesperson for the Grappa Center for Excellence in Gravitation and Astroparticle Physics at the University of Amsterdam. She shared in the 2016 Special Breakthrough Prize in Fundamental Physics for her role in LIGO, that's the gravitational wave detector, and this year's New Horizons Prize for developing new techniques to extract fundamental physics from astronomical data. I think that's kind of interesting, extracting fundamental physics from astronomy. I just find that very cool. So again, we've got sort of experimentalists on the ends here and our theorist in the middle. I want to start very simple, very broad, and just ask this question about what are black holes? And Andy, maybe I'll throw that one to you. Fundamentally, what are these things?
Well, if you have, so for example, on the Earth, if you have a rocket ship wants to get off the Earth, you've got to get it going at 11 kilometers per second. And then if there's no friction, it will go on forever and will escape the Earth, and it will disappear into outer space.
It needs that extreme speed, 11 kilometers per second, because otherwise gravity would pull it back.
Otherwise, gravity would pull it back. On the Moon, it's easier. You only have to go 7 kilometers per second. But if you have too much mass in one place, you have to go faster than 186,000 centimeters per second, and that's the speed of light, and nothing can go faster than the speed of light. And so, according to Einstein's theory of relativity, it's really a very simple consequence of it, that if you have too much mass in one place, nothing can get out, not even light. And that is exactly what Shep, didn't see. There was a black hole where they saw nothing in the middle of that beautiful image.
Now, I just want to follow up with this question that light doesn't have mass, so people might tend to think that light wouldn't respond to gravity, right? Which is typically thought of as this attraction between masses. And yet, light is affected by gravity.
Light has energy. We use it to power things. You can shoot a light beam up and it will hold the paper up. In fact, they're planning to make spaceships in that way.
So it has energy, and because of that...
It has energy, and anything that has energy is subject to gravitational attraction.
Mm-hmm. Can I add one thing to what Andy said? So we were asked what a black hole is, and you gave kind of a definition of an event horizon. But I didn't hear singularity in there, right? So there's, when I think of a black hole, I think of matter collapsing into a singularity, and then the event horizon forms around that singularity. So and there's two different things going on here, right? You've got the singularity where all the laws of physics break down, where the things we heard about from supergravity, where GR and quantum mechanics have to finally shake hands together, right? And then you've got this event horizon, which can be much farther away, which is very macroscopic. That's kind of what I study. I study the very boundary of that, and that's where the light can't escape. But some of the secrets are deep inside. Right?
Some are deep inside, some are just inside.
I love how metaphysical we've gotten
we
just
can't-
so briefly into this panel.
We can't even get a micron inside the horizon. So what you've seen, we believe that deep inside there is some kind of singularity where the force of gravity has become so strong that the matter just kind of went insane. But already, just right at the edge of where you could see, just beyond that edge, are things that we've just really been unable to understand. That's what's so wonderful about it.
Let me see if I can paint a picture of a black hole. Not like the image that you've captured, but kind of what you're discussing there. So,
Yeah.
Andy, I heard you talking about when you have too much mass in one place and mass goes crazy. I think I'm quoting you correctly, right? So essentially, like if you concentrated a ton, like 30 solar masses into a tiny point, right? That is your singularity.
Yeah.
That's kind of like your divide by zero point where, everything goes nuts and we just don't know. And that's why we call it the singularity.
Yeah.
I just want to demystify that word a little bit for people who, hear people throw it around. But it really means, such an extreme place in our universe that the physics doesn't, you can't really describe it.
Right.
And then out some distance from that, you have essentially a sphere, which would be the event horizon, which is this point, as we're saying, if you're inside there, we can't get any information because light can't come out from inside that sphere.
Right.
So it's not like a hard sphere or anything, but it's a sphere inside which, is this fair? Is that a fair picture?
It's fair.
Okay. Let me ask another question about, what are the different sizes of these things?
That's more for Samaya.
Samaya, yeah.
So in terms of the masses of
The masses and the sizes, and how does the mass relate to the size?
excellent question. I'll first, I think, sort of briefly map out, I guess, the kind of the masses that we expect for astrophysical black holes, and those are the sort of the black holes that I personally am interested. But I think Andy can talk about the more theoretical physical black holes that, as a theoretical physicist. But in terms of the end states of stellar evolution, in terms of massive stars, we're expecting kind of black holes potentially down to a few solar masses, being formed basically from the end of supernova, massive stars basically collapsing, going supernova, and there being their mass being so great that they eventually form a black hole. And up to sort of 50, 60 solar masses in terms of what one can anticipate to have from just, this basically collapse of the massive star. But as we've seen from the LIGO detections, you can get these mergers of black holes that are forming black holes that are heavier. And then there are astrophysical black holes that we expect from intermediate black holes. We have yet to actually detect these or observationally detect these, as well as supermassive black holes, and these are the black holes that the Event Horizon Telescope actually observed, which are happening, at the million solar masses to 10 to the 9 solar mass sort of range. Yes, so I think that's sort of the zoo of astrophysical black holes that we either directly observe through the light, as well as from gravitational waves that we're seeing at the moment. So I'll let Andy talk about, I guess, the small black holes.
I think it's worth emphasizing, right, that black holes vary dramatically from
size.
The mass of the sun to billions of times the mass of the sun. And so when we talk about a black hole, we could mean kind of very different size things. I don't know if you want to.
So let me say a couple of things. I think Samaya said it very well. You have this huge range. And I was talking to somebody earlier, I think maybe David Julius, and I was explaining that the LIGO detections and the Event Horizon Telescope detections are kind of like saying that a mouse is the same as an elephant. Right? You think about it for a minute, I guess they have feet, and they have a smell thing,
mammals.
and one has a big long trunk, and one is like a little quivering like nose. But they're the same kind of thing, right? And it's amazing to me that the black holes that Samaya is seeing with LIGO are the same from an Einstein's perspective as the one that is 1 billion times more massive that we're seeing with the Event Horizon Telescope. And if you took the Earth and you scrunched it into a black hole, it would be about an inch across, like a couple of centimeters across.
The size of
right?
a grape, I think, yeah.
And then it scales with mass. So the size of the black hole just scales linearly with mass. And so if you get to 1 billion solar masses, then you're looking at something that's bigger than our solar system. So that's the zoo that Samaya is talking about ranges in that way.
Right.
But it is a strange prediction of the Einstein equation that essentially the only thing that is different about black holes of different sizes from a micron up to millions of miles, they're just bigger versions of the same thing, with round, maybe they have some spin, but they don't differ otherwise. And that's very curious and difficult to reconcile
And I
feature
think
of
that
black
is one
holes.
of the most beautiful things about black holes is that they are kind of our simplest unit that we have in astronomy, in the sense that you only really need 2 numbers to describe them. Yes, their mass and their spin, at least in terms of the ones that we expect to be there astrophysically. And I mean, that's just incredible when you think about the entire cosmos, yes, that there are these objects where you can just entirely describe them by 2 numbers.
It's not like a star. Every star is different. Every star has different chemical composition, and the molecules are moving in different ways, and has sunspots and all kinds of complicated epiphenomena. A black hole, its mass and its spin, that's it.
So my understanding is that our galaxy is kind of littered with these stellar mass black holes, the ones that are similar in mass to our sun. Can you give me a rough ballpark for how many are out there in our galaxy? How many stellar mass black holes are kicking around in the Milky Way? Is there a ballpark?
Millions.
Millions? On the order of
there's-
millions? But when you went to image one, you didn't look at one of these stellar mass black holes. Do you want to talk about that and why you picked the targets that you did?
Oh, yeah. The zoo of black holes is pretty broad. We attack them in different ways. And the reason we attack them is because they're the best cosmic laboratories we have. If you want to look at where the theories break down, you want to go to the most extreme laboratories. That's why we're all doing this, I think. In experiments of the mind, as with Andy, or with different telescopes, as with us. The reason we went to these large black holes for the Event Horizon Telescope is because they're the only ones big enough that we can see. We could never get the angular resolution with any telescope that we have to see and image a stellar mass black hole. It has to be a supermassive black hole. And there are only 2 of them that we know of that we can do this with. There's Sagittarius A star, which is a 4 million solar mass black hole in the center of our galaxy. And that's about 50 micro arc seconds across. So the whole shadow is 50 micro arc seconds, which is the size of a grapefruit on the moon. And we have another one, which is the M87, which is one we did image, which is a little bit smaller than that. The next biggest one is so small that we could never hope to do that yet. But if we launch a satellite into space and we orbit the Earth or go out to some larger distance, then we could bring a lot more black holes into range.
And perhaps let's briefly address the question of, if you're trying to image something that's totally black, how do you actually image it? Like, how do you get a picture?
Yes, so it turns out that black holes are attractors, and all this gas and material is trying to get into them, and they're trying to get into such a small volume that they naturally heat up to billions of degrees. So in a paradox of their own gravity, black holes tend to shine very brightly because this gas, just before it goes through the event horizon, is very, very hot and glowing. So we are seeing with the Event Horizon Telescope the last glow of material before it disappears through the event horizon. And that allows us to make that nice measurement of the photon ring.
And what have we found out by doing these different types of astronomy, both using electromagnetic waves and now using gravitational waves? what have we been able to really determine and uncover about black holes? Samaya, what are the big sort of last 5 years?
So I think from gravitational waves, the unique probe has been, if you assume general relativity is correct, inferring essentially the masses of these stellar mass black holes. Actually, the first event was surprisingly much heavier than we had anticipated from just looking at X-ray stellar mass binaries, for instance, in our galaxy. They had, the two black holes had masses of 29 and 35 solar masses, and this was actually a surprise in terms of, well, some people will say they also predicted this, but it was actually quite astounding when you compare it to the previously known X-ray binary black holes that were inferred basically from the electromagnetic radiation around there. So I think having a unique probe, a different way of actually measuring the properties such as the actual masses and not having to depend on the actual astrophysical model, which includes a lot of complicated nonlinear physics when you actually model basically the emission that you expect for X-ray binaries, where you have a star which is being basically orbiting a black hole, and so that's how you're inferring the mass. There are a lot of assumptions that you have to assume in terms of the accretion disk, exactly how the matter is being accreted onto the system, whereas with gravitational waves we had this unique probe onto the masses. One of the hopes is that as the instruments get more sensitive with higher signal-to-noise ratio, if we're also able to observe more cycles in band of these systems, we will maybe have information, for instance, about the spin. And then I think the next big question will be answering actually how do these systems actually form? How do stellar mass binary black holes, where do we expect them to, do we know that most massive stars are actually in pairs, but it's unclear whether the ones that we've seen have been formed dynamically or else in isolation, for instance, in the galaxy. And so all these questions, I think, will be answered, as we move into the era, as we are doing, in terms of population statistics.
And Shep, from getting that image, what could you determine about black holes? I mean, when you go to image a black hole, James Corden made the joke yesterday that your image looks kind of like a hole, a black, it's kind of like what you'd expect. It was humorous, right?
Everybody's a comedian.
Right? Yeah, well, James Corden in particular. Right? But I think that...
Who would have thought a comedian is funny?
But I think there's a serious question which underlies that joke, which is, what could you have seen if not what you saw?
So I think that's a really good question. I want to get back to the title of this session, which is, will black holes give up their secrets? And the question is, what are the secrets? Like, what do we hope they'll give up? And I'll tell you a little bit what I think some of the secrets are, and I think Andy holds the key to some of the other secrets here. But so you ask yourself, can we test Einstein's theory, right? In the one place where Einstein's gravity could break down, where we can see it, does it? So that's one secret that we're trying to get at.
In the most extreme gravity regime,
right?
Does this theory still hold
at the edge of a black hole? So Samaya, with the LIGO mergers, has seen that ring for stellar mass black holes. We saw it visually, and to the extent that we can make these precision measurements, we've confirmed this photon ring, that this is the ring that photons are actually moving around in an orbit around the black hole. We've measured that with a yardstick, and we've reported it back to Einstein, and he's given us an A on our paper, which is kind of nice.
Or is it you giving Einstein an A?
No, we don't do that. No, he's the grader, we are the pupils always, right? And let's not mess with the Einstein.
Hey.
Yeah. And but then more than that, then I look outward and I think, how do black holes, despite being the smallest objects predicted by Einstein, how do they, power these jets that can pierce entire galaxies and change the night sky as we know it? And to understand that, we have to look at the magnetic field structure around the black holes, which is being torqued up, and like an egg beater is flinging things out at light speed from the North and South Pole. Nobody knows how that works. And so in order to understand the secrets of why the night sky looks the way it does, we have to see how these engines at the centers of galaxies do what they do. And that's what the Event Horizon Telescope is going to be focused on in the decade to come. You know, all the wisps I was showing before, like those are very important. Like how does the black hole make things orbit around it? How does it expel all this energy? But then in terms of secrets, what I'm very interested in is looking inward and understanding where all the information goes. That's all. It's an entirely different universe. That's why black holes are so exciting. They affect things on large scales, but they also plumb the limits of what we know about fundamental physics.
And I wonder, Andy, if this gets to the idea that there's kind of paradoxically, we believe, black holes which suck everything in, and yet they also have a mechanism for evaporating, for giving out what was inside them. Do you want to talk about that?
Yeah, I'd like to, though, add a little perspective that hasn't been in the discussion so far. So the black holes were discovered 100 years ago. They were predicted 100 years ago. And people have been arguing continuously for the last 100 years about what a black hole is and what's inside it and how it works. And for most of that 100 years, there seemed to be no consistent answer to various versions of that question, so much so that many people, including Einstein, who wrote in 1939 a paper that black holes don't exist, they're too weird. And so it really is a historical moment. I mean, humbling for me to be sitting beside these giants who saw, for the first time in 100 years, in different mediums, a black hole. 100 years, we've been wanting to see them, now we saw them, they're there. And of course, that made me feel good because I've been working on them for 30 years, and I'd hate to think that the thing I was working on for 30 years didn't exist. And the puzzles that they present, the things that Einstein worried about, I think we understand. The work of Hawking and Penrose and so on explained that. But then there's the quantum puzzle of black holes, of all the information that's in the black hole and how it gets out. That is a deep puzzle that we're not going to solve this year, but we do have to, see the black holes before we can measure them. And of course, the measurements haven't told us how to solve Hawking's puzzle about quantum information. But you have to see it, a basic image of it, before you can see the more detailed.
So I wonder if
and we'll get there eventually. And it is an amazing thing that this is the moment in which I think black hole theorists and black hole observationalists are now talking together. Shep and I wrote a paper together a couple months ago. And so we don't know where we're going, but we're talking and we're thinking about the experiments and we're trying to understand it. We don't have an answer.
Yeah, sorry to interrupt.
Well, I was just curious if we can nail down this idea of information any clearer for this audience.
Well, there's a in his famous paper, Stephen Hawking wrote a paper which said that there is some insane number of gigabytes inside a black hole, enough so that the Google data banks would fit inside a black hole a trillionth of an inch. That's if you take into account quantum effects, you infer that black holes are the best hard drives in the universe. Now, this contrasts with what Einstein and Schwarzschild told us, and which we were discussing a moment ago, that black holes are featureless objects which don't even really have an interior, and they don't store any information. So there's a basic paradox where two different ways of looking at the same system lead to the opposite conclusion. And that is a fundamental paradox in modern physics, and many people are trying to resolve it and have been for decades, and we will solve that problem.
You're confident?
Is that a prediction?
Yeah, that sounds like a prediction.
We solve because we solve every problem, and there hasn't been a problem in science that we just could never solve. Sometimes it takes a long time.
Except the ones that haven't been solved yet.
Except, well, we'll get it. There's no reason we can't get it. You know, I'm not saying tomorrow, but we'll get it.
And when we do, that'll be worth a breakthrough prize.
Maybe several.
Oh, yeah. but the cool thing, when Andy said that we're writing a paper together, it's true. There's been some great work by a student and postdoc in Andy's group, and by somebody in the Event Horizon Telescope, Michael Johnson and Alex Lupsaska. And they together, they have been looking at what happens right at the boundary of the black hole. And it turns out that light can go around half an orbit, and that's mostly what we see with the Event Horizon Telescope. But then some of the light just continues on and makes another orbit. And then it makes another orbit. And it turns out that close to the black hole, you wind up with an infinite number of nested orbits, and they all have images imprinted on them of the universe.
And we're going to see it. See the look in his eye?
Yeah.
Now, I just want to say, so things get so weird around a black hole. Like, imagine that. Around a black hole, you've got nested images of the entire universe going back for all of time, right? Now, they get fainter and fainter as you go around, right? So every time they get exponentially fainter, and you think to yourself, wow, I can never see that. Now, that's where the gold is, right?
Yeah, yeah.
Not just in the neutron star mergers, but if you build an interferometer, if you take a telescope far from the Earth, let's say at the Lagrange point, and you pair it with the Earth, then you get such high angular resolution, like 0.1 micro arc seconds. Now you're looking at, I don't know, like what's on the moon, a grain of salt on the moon, or even smaller than that. Then you might be able to start teasing out these nested rings of emission that were the subject of this paper. And then you can really start to look at the spin of the black hole. Just instantly, you get the spin of the black hole. You know, instantly, you understand all these tests of Einstein. So when we talk about the secrets of the black hole, I'm enthused because of the ingenuity of what we can do and the theory that's coming to explain some of this stuff. And that's the intersection I think is going to be very fruitful.
You know, Einstein taught us that space and time are not what we thought they were. It gets curved, it does weird things, and he explained little effects like bending of light by the sun and the precession of Mercury's perihelion as effects of the curvature, weird curvature of space. But when you get to a black hole, it's really curved. And the world around a black hole is really different. It's not like our world at all. And now we're seeing it.
Well, I would love to continue this conversation for another hour. I think I could definitely get sucked into this particular black hole. But our time is up, and so we will have to say a huge thank you to our panelists. Please join me in thanking them.